Our next speaker is Professor Raghurajaram Pandyan sir from Nit Warangal, who will present on the development of carbon-epoxy semi-cured composite laminates for applications in aircraft structures. Sir research interests include advanced polymer composites, liquid composite molding processes, material process modeling, and polymer nanocomposites. Sir is currently the PhD coordinator in the Department of Chemical Engineering at Nit Warangal. He is also involved in several key roles, including Professor in charge of the Chemical Engineering Colloquium and Mass Transfer Lab, and Treasurer of the Chemical Engineering Student Society and IICHE Student Chapter. His ongoing research projects include developing aerodynamically stable thermal protective systems using hybrid nanofilled carbon composites and 3D printable composite thermal sheets. With extensive experience in various research and consultancy projects, Sir work focuses on the development and optimization of composite materials for high performance application. His talk will provide valuable insights into the advancements in carbon epoxy composite laminates and their potential uses in aircraft structure. We welcome you, sir.
So, thank you, Prof. So, for your generous introduction. Thank you. So, I think I need to do dual role today as a tail ender watchman, or or first is tail ender watchman, or to pinch hitter, right? Yes. Yeah, I need to pinch it, right? I have to complete within speculated time. So, my topic is development of carbon-epoxy semi-cured composite laminates for applications in aircraft structures. So this is a part of work in developing one-shot thick-sectioned integrated composite, which is funded by extramural research scheme of DST. So here comes the definition of the problem. When you come to aerospace composite laminates, two restrictions are there, bottlenecks are there. One is we cannot manufacture a composite laminate having a thickness more than 12 mm. First one is. Next one is you have to have a pore volume less than 0.01% as per the Airbus standards. And generally, if you see in Airbus, we manufacture autoclave this thermoset composite parts using autoclave molding. But the problem with autoclave molding is it is costly technique and it has part size limitation, because you can maximum manufacture a part size to the part size of the autoclave molding. Next one is it requires higher processing time and it has lesser production rate, and you need to have a skilled laborer and you need to have skilled designed tool to withstand pressure and temperature. So obviously, when you manufacture a composite laminate for aerospace structures, you should have a uniform resin fiber volume fractions, uniform product thickness, reduced porosity, surface properties, and dynamic load bearing capacity. So as I told earlier, it is a part of development of one-shot thick-sectioned composite laminates. So this is development. How we are making the thick section, one-shot thick section composite parts is by development of thin-sectioned semi-cured composite laminate. Then we, using thin film adhesives, we co-cure thin-section composite laminates and to manufacture the one-shot thick-section composite laminates. So the main advantage of this. I mean, not to change. The pointer is not there. Okay, fine, no problem. So if you see the bottom figure, so you can co-cure two different laminates. So which will be helpful in two ways. One is it can have dynamic loading, it can bear dynamic loading, and it can bear a differential loading. So you can apply dynamic loading as well as differential loading. You can apply two different types of loading on both ends of the thick section integrated composite laminates. And once it is co-cured and it is made as one single component, you have to do the quality estimations. Okay, so this is the total methodology. First, to prepare the semi-cured composite laminates, first of all you have to read the thermal characterization of a resin through differential scanning calorimetry. From that you should obtain time temperature cure window for the resin. Then you have to develop the semi-cured prototypes, semi-cured composite prototypes through different molding techniques, and you have to use those semi-cured composite laminates, and with the use of thin film adhesives you have to co-cure and you have to make the one-shot thick section composite laminate. So I will be dealing with the thermal characterization of resin in the later part. So when it comes to quality estimation, first of all you have to find out adhesive bond strength. So next one is for the semi-cured panel, which is of our interest. You should go with surface contaminations through XPS, and you should do porosity analysis using optical microscopy and X-ray tomography. Then you have to find out, like, I manufacture the semi-cured composite laminate and I can transport to somewhere else and I can produce the thick section composite laminates in situ. For that I should know the storage capability. How can I store the semi-cured composite laminates? And I should find out the panel homogeneity through cure volume for cure degree of cure measurement as well as Favre volume fraction. So with respect to different dimension, you have to find out cure volume, cure degree of cure as well as volume fraction. That should be uniform with the distribution. Next one is you have to analyze the resin bleeding. So when you transport, obviously you may transport with the layers with a certain pressure. So you should know how much resin is getting bleed out when the laminate consistency is a semi-cured one. So as I told earlier, I have used RTM6 resin because it is for aerospace composite laminate. So when you go through any resin product data, the manufacturer will not give you any detail about the mechanism of curing. That means you never going to get the data of time temperature cure. That means if I apply some kind of cure cycle, say 140 degree for 5 hours, what may be the degree of cure? So generally we may not need this data because we tend to cure the composite laminates 100%. Whatever data it is given prescribed by the supplier, we will be utilizing, and we say that the composite laminate is 100% cured, which may not be true. But in this case, I have to prepare the semi-cured composite laminate. I need to know the complete cure knowledge to the applied cure cycles. So for that, what you have to do is you have to apply differential scanning calorimetry method. At first, you have to perform the thermal characterization, dynamic thermal characterization through DSC. That means 10 degree per minute ramp. You have to do it from the room temperature to the or storage temperature to the 400 degrees centigrade, maybe thermal degradation temperature of resin. So in that, what you can obtain is, since the resin curing is exothermic in nature, the heat evolution behavior is recorded as a function of time with respect to rise in the ramp temperature. So you will get, at first you will get heat flow as a function of time at different temperatures. Next one, from that figure you have to find out what is the onset temperature of curing at the peak temperature of curing, and you have to select at least 5 different intermediate temperatures to conduct the isothermal study. Generally in composite curing we used to perform at isothermal temperatures because we don't want differential cure evaluation within the part thickness. So that's why it is prescribed to cure the sample at isothermal temperatures. So to understand what may be the ideal temperatures, isothermal temperatures to cure my resin, you should perform the non-isothermal study, and you should find out what is the onset curing temperature and the peak exotherm temperature, and you should perform in between 4 temperatures. There is one another truth behind it, that is that when I perform the temperature which is lesser than the onset temperature at DSC, it takes a lot of time to complete the curing reaction, so that the sample has to be retained within the sample holder of DSC for hours. But when I keep the temperature more than peak temperature, before the DSC machine senses the heat flow, substantial reaction might have been completed. So obviously you should select some temperature in between, at least 4 to 5 temperature between the onset cure temperature and the peak cure temperature. So once I perform the isothermal DXC experiments, you will get a plot of heat flow as a function of time at a different isothermal temperatures. So I can get a degree of cure from this plot by having partial area divided by total area. Total area will be giving you heat of evolution, total heat of evolution, and the partial area will be giving you the heat at the particular time. So partial area divided by total area will give you the degree of cure. Once I get the degree of cure as a function of time at a different isothermal temperatures, I have to take slope of every instantaneous time, and if I plot it, that will give you d alpha by dt, which is nothing but rate of cure. So rate of cure using classical curing kinetics equations, rate of cure is modeled as a function of temperature and degree of cure. That will give you the classical curing kinetics modeling. So from the curing kinetics modeling, you have to extrapolate the kinetic parameters from the lower end temperature to the higher end temperature, where the prescribed temperature zone is prescribed for your resin. You can extrapolate those parameters and you can produce time, temperature, cure window for any type of resin. Let me see how it is developed for RTM6 resin. So as I told, I have performed the isothermal curing studies at DSC at ramp of 10 degree per minute. So you can able to see 3 plots are there. So you can able to find out what is the onset temperature, what is the peak temperature, and you can able to see that the onset temperature is almost 160-170 degrees centigrade, and the peak temperature is almost 240 degrees centigrade. So I can take a reading like isothermic curing temperatures can be conducted at 4 different temperatures, 180 degree, 200 degree, 220 degree, and 240 degree. That is what performed in isothermal DS experiments. You can able to see that 180, 200, 220, and 240 degree centigrade. And I got the heat evolution behavior. Once I get the heat flow curve, isothermal heat flow curve. So once I discretize partial area by total area, I can able to plot degree of cure. So after getting the degree of cure versus time for different isothermal temperature, again I can differentiate, I can get it d alpha by dt, which is rate of cure. That rate of cure is plotted as a function of degree of cure to fit into classical cure kinetics modeling. Here we fit into 2 different models. One is Kamal and Sarur model, which has 4 parameter model, and modified Kamal and Sarur model, which is 3 parameter model. Whichever lowest parameter model fitting too good, which will be taken as the best model. Here modified Kamal and Sarur model, d alpha by dt is equal to k alpha power m 1 minus alpha power 1 is taken as the ideal model, and it is exactly fitting, having more than correlation coefficient, it's coming more than 0.9. So with the kinetic parameters k, right, as a function of temperature, I can extrapolate kinetic parameters. What are the kinetic parameters? Arrhenius equation, that is frequency factor and the activation energy. Using those 2 factors, I can extrapolate, and I have defined the complete cure process window for the RTM6 resin. You can see it is defined from 120 degrees centigrade to 200 degrees centigrade, and time is like few hours. Like if I choose my cure cycle as 140 degrees centigrade for 3 hours, without performing my experiment, from this data I can extrapolate and I can say this is my degree of cure. So with only 4 different data, I can explore complete kinetics of RTM6 resin. So now obviously we have performed DSC for resin, but what we interested is that semi-cure of the composite panel. Since composite consists of carbon fiber and RTM6 resin, so we may expect that the carbon fiber may offer some resistance for the heat transfer and degree of cure. So that's why we have to check whatever cure evaluation behavior of the composite panel is to be compared with the cure evaluation behavior of the resin. So we have performed with respect to hot press process. So here we have used RTM6 resin, carbon fiber fabric of G0926 with 5H satin U, and matte architecture of 6 layers at 90 degree, 90 degree, 90 degree. These are the parameters took from Airbus. Then we have checked actually with respect to our previous plot. We thought like the cure cycles with 160 degree centigrade, 140 degree centigrade with a different time interval will give us optimistic results related to semi-cured panel. So that's why we are going to give 160, 140 degree centigrade with the time intervals we will be exposing in the hot press process, and we try to study what will be the degree of cure of the composite panel. So if you know the composite molding processes, actually there are two. One is RAM zone. RAM zone is like if I have to go to 160 degrees centigrade, you cannot go to 160 degrees centigrade straight away. What we have to do is you have to use a RAM from room temperature to 160 degrees centigrade. Then you have to put a platform of 160 degrees centigrade for isothermal temperature for given time. So here we have used ramp of 10 degree per minute from 100 degree to 160 degree. And at isothermal temperature, it stays for 160 degree for 1 hour. So we will keep this cure cycle and we try to find out what will be the cure of composite laminate. So if you compare the cure evaluation behavior of the RTM6 resin as well as the laminate, you can able to see that the RTM6 cure resin cure is lesser compared to the composite laminate. So obviously in the earlier stages I told that so carbon fiber can give you some kind of resistance for the heat transfer, and it is expected that the degree of cure should be lesser than the resin, but it is just opposite in compression molding. So what may be the reason? Because when you do the resin characterization in DSE, so whenever heat get evaluated in DSE, it is vented out by the nitrogen purge. So no heat gets stored inside the pan, in the pan, okay, DSC pan. Whereas in the compression molding, so obviously the sample is completely closed, right? It's with a metal mold. What will happen when the heat get evaluated? It get trapped inside itself. It get trapped. So when heat is getting trapped, since it is exothermic in nature, more heat is getting evolved and it is trapped inside. Actually, the temperature of the sample is much more higher than the applied temperature. So that's why the curing of composite laminate is higher than the resin cure. It is the case of 160 degree centigrade. So when you go to 140 degree centigrade, the same trend is getting observed. So another important thing is that I have to manufacture semi-cured composite laminate and I have to transport it. So there are two important parameters. One is degree of cure and the physical consistency of the laminate. So when I cure to lesser curing, certain cure like, so when I have a curing of 30% degree of cure, what will happen? It is very tacky in nature, it is very flexible. So this is very smaller sample, that's fine, you can able to extract it up. When you do it in a real RTM mold, when you extract, what will happen? Since it is flexible, the dimensionality may not be get retained. But when I go for higher degree of cure, for an example, more than 60, 70 degrees centigrade, it is more disadvantageous because we said that to produce thick section composite laminate, we will be having thin adhesive film and we will be co-curing. So when this semi-cured composite laminates degree of cure is more higher, there won't be any interfacial curing. Interfacial bonding you may not expect with the thin film adhesive. So you should have a trade-off between degree of cure and the flexibility of the panel. So obviously Here the gelation is very, very important point. Obviously, you know what is resin gelation. So where it get convert from the gel state to the rigid solid state. So you should find out when this resin is getting to rigid solid state at what degree of cure. That you have to check. In both the cases, it is coming 40%. 40% degree of cure, it becomes rigid. So when you make a semi-cured composite laminate at more than 40 degree to 45 degree of cure, it is ideal so that you can see that it has a minimum degree of cure and it has the physical consistency. It is not more flexible or tackiness. So obviously we have tried out with the RTM also. So this is not simply a RTM, this is vacuum enhanced resin transfer molding technology. This mold we have developed on our own. So we have a resin tank also, which is because at room temperature RTM6 is rigid solid, right? So you have to have a preheating temperature 120 degrees centigrade. Before you inject the resin, you have to rise to 120 degrees centigrade so that the resin melt and it will have a flow consistency. So these are some of the mold parameters. Obviously, you have to use peel fly so that you can extract the panel from the mold. So it is designed for 60 mm to 600 millimeter to 300 millimeter dimension. So again for RTM, so first we have checked with hot press process. Next one is with respect to the RTM process. Same material we have used, but only the dimension has been varied, 600 millimeter into 300 millimeter. So mold release agent is Loctite free coat, which is supplied from Henkel, and peel plies polyester and Diatex. These two brands were being used, and the thin film is used as epoxy adhesive FM 300. So these are very, very important parameters. This also we took the consult from the Airbus. So we tried out with the RTM process, and first of all, you know, as per the resin supplier cure cycle, 180 degree for 120 minutes. So for 2 hours, we kept it for 180 degrees centigrade. So we got the degree of cure is almost 99%, and we have done one more time. So to get the repeatability, so it has 8 layers. So again, we have gone for semi-cured composite laminate production. So first we have taken cure cycle of 140 degrees centigrade for 30 minutes. So we got degree of cure as 15% and panel thickness of 2.6 millimeter. And with second one is 140 degree for 60 minutes, you got degree of cure is 15 minutes. So 140 degree for 30 minutes got you 15%. And 140 degree for 60 minutes got you 21%. So again, for a different time factor, 140 degree, earlier 30 minutes, 60 minutes, 90 minutes and 120 minutes. And calculation here is 30% and 38% respectively. So you can see that cured state is semi-cured. So with the usage of peel ply also, because we have used different peel ply, this also may have certain hindrance for the heat transfer from the mold surface to the panel. So with no peel ply, you get a degree of cure for 160 degree 45 minutes, 53%. But with the polyester peel ply, you got 56%, and Diatex peel ply, you got 55%. So obviously, you can see that polyester is, it is also as like what we have defined in hot press process. Same phenomena is happening here. That's why this degree of cure is little higher. So you have to obviously, as I told earlier, again we have to have a trade-off between the degree of cure and physical consistency. So this is the semi-cured panel cure evaluation. So obviously I didn't given a data like with the experimental result, like what is the difference between the cure evaluation behavior of the resin as well as the panel. So we have found out one model which will tell you what will be the cure differences. So we have done lot of experiments and we compare the cure evaluation behavior of the resin as well as cure evaluation behavior of the panel at different thicknesses we have evaluated, and we have made a model such that it will predict you if you increase 5 to 10 degrees centigrade other than the designed cure cycle. Obviously the cure differences between the laminate and the resin, neat resin differences can be reduced, which I mean that the composite panel will behave like the resin cure. So we have found out the model. We will tell you at what degree has to be increased. Say for an example, if I am applying 150 degrees centigrade for 30 minutes for the resin cure, for the resin curing, so what will be the cure cycle has to be applied to the composite panel such that you will get the ideal curing. Say 30% ideal curing, it will happen with the resin as well as it will happen with the composite laminate. So after that we have to go for the quality measurements. First one is cure evaluation and thickness variation and water ingestion. So water ingestion is very simple, like what will be the change in the weight. So next one is how the degree of cure varies with respect to room storage. Simple room storage, I am not going for cold storage. At normal room temperature, what will be the change in the degree of cure if I store it for 4 or 5 days. So you can see that it may be a smaller variation. So we can say that like there is always a thermal stress that is induced within the composite panel, which may add to rise in certain degree of cure. So generally because RTM6 resin is thermally activated resin, you doesn't need any curing aids. So you doesn't need initiator or accelerator to cure it. Whereas if you apply temperature more than 180 degrees centigrade, it will automatically starts cure. You cannot stop it after all. But you can reduce the rate of curing by reducing the temperature. So at every temperature, once it is thermally activated, some degree of the curing will be happening. So it may be the chance that there may be some residual heat there in the panel at room temperature, which will be the reasoning for the slight increase in the degree of cure. So this is again with respect to refrigeration. So refrigeration means it is to be at -5 degrees centigrade. So this is also very smaller difference only it is there. So what I can conclude is that whatever semi-cured panel you are manufacturing, you can store at either room temperature or at cold storage. So generally we do it at cold storage only. So to measure the homogeneity, panel homogeneity, so for 300 dimensionalized composite panel, so we have taken 3 samples. One is as mentioned 75 mm, 150 mm, 225 mm. There we have extracted the samples, and we have done 2 things. One is we have analyzed for degree of cure and fiber volume fraction. So from the table you can understand that we analyzed 2 different panels. With the panels at the mentioned dimensions, you can see that there is no appreciable change in the degree of cure as well as fiber volume fractions. So this is simple optical microscopy. When we could not able to afford for high-end pore volume analysis, you can go for optical microscopy. So if there is any macro pores, you can easily able to obtain from the optical microscopy. So this is simply composite fully cured as well as semi-cured. So generally what will happen is, so there may be change in the porous nature with respect to degree of cure also. So that's why we try to find out whether there is any pore volume change with respect to semi-cured and fully cured panels. So we have done with X-ray tomography also. So as we said, like it is to be less than 0.1% pore volume. So it is 0.014%, which is very much appreciable. So this is for 40% cured composite panel without peel ply. So you can able to see that whatever the red points are there, those are this thing pores. So what we are concluding here is that, so irrespective of going for autoclave molding, we have used vacuum enhanced resin transfer molding. So this is not simple resin transfer molding, there is vacuum enhanced resin transfer molding. Whereas in the injection port, you will have the injection pressure, but at the exit port, exit vents, you will have vacuum attached. So with that process, what we have achieved is we can able to manufacture aerospace grade within RTM process itself. So since this is the very important parameter where you should have less than 0.1% pore volume, we can able to achieve. So this is for 100% cured composite panel. This is also coming very less pore volume percentage. This is volume percentage actually. So for 60-degree cured composite, so we try to find out what will be the change in the pore volume percentage with at different cure level. So for 100% cure, again it is 0.006%. So there are certain observations. So obviously it is required to cure the composite panel to a minimum degree of cure, say at least 30% of curing. Otherwise, the extraction of panel from the mold becomes difficult. Extraction of under-cured panels using forcible means can lead to panel damage and alteration in panel dimensions. So obviously we know that the strictness in the dimensionality for aerospace grade composite panels. So then proper mold sealing and sealing thickness should be ensured. Obviously, if sealants are not matched properly, there will be bubbles entrapped. So obviously what will happen? That part has to be rejected. The next one is the composite panel cure may differ to the different trials of same cure cycle. If resin preheating, mold filling time differs. So you should standardize everything. So obviously if I conduct the same cure cycle, first time, second time, you can have a differential cure, composite panel cure, because there may be difference in resin preheating time. Hence, care should be taken to ensure the idealistic resin preheating and mold filling time at each trial. Also, uniform resin conditions have to be maintained during storage and preheating stages. Even the resin, neat resin also has to be cured at conditioned process. So that's all about my presentation. Here, I just wanted to say what I am doing at my lab. So I have 4 different projects, sponsored projects. One is of design of aerodynamically stable thermal protective systems using hybrid nanofilled phenolic carbon composite ablators. It is from core research grant. It is granted in 2024 this year. So this is still next 3 years it will be there. And next one is development of 3D printable composite thermal steels. This we are doing it for Advanced Systems Laboratory, DRDO. So they are the collaborator. And we have research grant of 30.9 lakhs. This is also again CRG core research grant from DST sir. And next one is, it is combination of experimental from simulation tool, development of simulation tool in predicting the ablation behavior at rocketry, that is re-entry problem. So for re-entry capsule, we have composite ablator. We can predict what will be the mass loss percentage at the surface, how the composite ablator behaves at the aerodynamic loading. So that is for, this is from Spark, Minister of Education, having 45.42 lakhs, and it is sanctioned in 2023. And recently again one more project got sanctioned, development of cerium oxide based dispersion for functional polymer coatings from IREL India Limited. And this is of 41.88 lakhs, and just 2 months back it got sanctioned. So these are the ongoing research projects currently. So just to have a view of my lab. So we work on, I have currently 8 PhD scholars working under me. So they are working under different heads. One is advanced polymer composites. For mass transit system, we are developing components. And particularly right now we have mastery for the rocketry and space and rocketry composites. And we recently started working with advanced polymer coatings with the cerium oxide based. And also we are already started working on hydrogen barrier storage transmission coatings. Then 3D printing, just 2 years back we have started with 3D printing of neat thermoset resins as well as nanofilled thermoset resins. And my team has developed one COMSOL algorithm for optimization of curing as well as mold filling process. Actually we have published a few papers based on this software developed by us, one team. It is in-house coded. So we will be waiting for some more process, some more experimental validation. After that, we will try to keep it as open source. That will be helpful for a lot of small scale industries. So these are certain, there are several facilities available. Very importantly, I want to say that we have 3D printing facilities for photocure resins, neat thermoset resins, as well as nanofilled resins. And resin transfer molding is there, and we can have experimental setup. This is designed and developed by our team. Reinforcement mat permeability, which will give you Kx, Ky permeability data for any kind of fiber or any kind of test fluid. And we have another beautiful equipment, weathering chamber, that is simulated weathering chamber. We can simulate light intensity, the water spray, that is humidity and temperature within that simulated chamber. And we can find out the aging process in the composite material, either it is biocomposite or any composites. So that ends my presentation. I'll be happy to face any questions available. Thank you. The chamber can go to 100 degrees centigrade. Yes, not zero actually. It will be room temperature to 100 degrees centigrade.